afternoon.
Oh, well. Better to have rain than no rain. Does anybody else have a class in here this summer? Because they should have a projector off when they come in. It's on. All right. We're into antennas, and I did a short dipole, and I put stuff about the loop antenna up there, right? Now, for the loop antenna, I want to make sure you know this, that I will always give you the equations for loop antennas. I mean, it's radiation resistance and stuff. And really, with antennas, what you're going to see is the key factors. There's only two things you really care about. One is the gain, or directivity, it's a function angle. And the second is the radiation resistance. Everything else, really, you want the electric field from, and you have those two. You find the power to the antenna. And as a matter of fact, why don't I just show you this right now? I've got notes for the lecture, but I'm going to just try to show you what I mean and why. Why it really. That's the tell-all. The rest, I mean, if you want the E field, we can get it. The H field, we can get it. We can get the beamwidth. We can get anything else if we have these two things. All right, so in general, for any antenna, I'm going to use a straight wire antenna. Any at all. There's going to be a certain amount of P radiated. That's the total radiated power in watts. You all with me on that? Now that radiated power is equal to 1/2 I naught squared. I naught is just the current going into the feed point of the antenna. It's this times the radiation resistance. We'll go through a few examples. So can you all see this, by the way? So with a short dipole, and I told you the only two things you really need are the radiation resistance and the total power radiated, right? Now here's why. Let's assume we have the power radiated. All right, we're going to assume we have the power radiated. And I want the actual power density, the average power density at some point. Well, I've told you before that the average power density anywhere would be the total power radiated over 4 pi r squared. Now that's just that's the isotropic power density, right? There's no focusing. If you know that if you say that the thing's isotropically radiating, you put so much power in, you just divide it by the surface area of the sphere, and you've got the power density at the radius r, right? Take this, and now you multiply it by the gain. The gain will be a function of theta infinity. And we know gain is efficiency of the antenna times the directivity of the antenna. I'm trying to be as clear about this as I can. This is how I think of them when I work with antennas. So if we have a short dipole, that's the general formula. By the way, if I have the average power density, that's in watts per meter squared, right? All right, that's also equal to 1/2, this is propagating fields, we're in the far field, 1/2 times the magnitude of the E field at that point divided by eta naught, right? It's in the radial direction power is propagating. And it's also equal to simply 1/2 eta times magnitude of the H field squared. So if you want E or H, and you have the power radiating, the gain, you got it. You tell me a distance r and you got it. You with me on that? Now, by the same token, if you have the gain as a function of angle, you can plot gain versus any angle, theta or phi, and you can see where it goes down by 50%, its maximum value. You can easily get the beam width, right? I don't want to even spend much time on that. I'm just trying to tell you you can. Ultimately, when we critique an antenna, we want to know the gain, the general formula for gain. We do antenna measurements, and we get mathematical statements that really approximate that. And then we need the radiation resistance. Now, for the short dipole, do y'all remember I calculated first the electric field, then I calculated the power density, then the total power radiated, then we got the radiation resistance. Do y'all remember? After we got the radiation resistance, I said that from that point on, the only thing you need to know is the current going in. This is at least what I think I said. The current going into the antenna, and if it was a short dipole, and the length. Now, the length had to be less than a tenth of a wavelength, a tenth of a wavelength or less, and then you've got it, right? And for a short dipole, you remember this? For a short dipole, you remember that the directivity was equal to 3/2 times the sine squared of theta, right? It's a peak when theta is 90 degrees or perpendicular to the antenna. You all with me on this? Right? You remember it?
That's directivity.
Yeah.
And that relates to beam width?
Well, if that's the directivity and the gain are together, right?
Right.
It's one is proportional to the other. Assume the efficiency is 100% or the value is 1, so directivity is gain. If you take this and put it in here, then you see these terms are what? Those things are a scalar value at a given distance r away, right? Mm-hmm. So if you were to plot this, you see that when the directivity has a maximum, when it goes down to 50% or 0.5, its maximum, you can easily figure the beam width, regardless of the mathematical functions. You all with me on this? Right? I mean, I'm just trying to tell you this, but the directivity of a short dipole is this. And do you remember calculating as 1.5 maximum? All right, maybe I better put it down as 1.5, right? Times the sine squared of theta. And by the way, this is for all short or small dipoles. Short or small dipoles. Now, once we have that, if I asked you a question, or if you were given a question, I got a short dipole. I suppose I got a short dipole, something where L, say, is equal to lambda over 20. I'm going to make one up. All right, L is equal to lambda over 20. This is a short dipole, right? It's less than a tenth of a wavelength. And we're going to orient this on the z-axis. And now I'm going to come out at an angle of theta equals 45 degrees. And there's two things I want. I want to know if the total power radiated, I'm going to just make something up here, P radiated is equal to 10 to the third watts. Then I want to know how far out I have to go before the E field, I want to know what R is, before the E field becomes, say, 1 millivolt per meter. So this is a typical, this tells me if you understand. I want to know the distance R, right? For the E field to go down to 1 millivolt per meter. Milli is 10 to the minus third, all right? I can put 10 to the minus third volts if you prefer. So I want this as 10 to the minus third volts per meter. So how do you do that? Just think about what I told you. I gave you I didn't even give you the radiation resistance. So you've got the P radiated, right? So well, we can do this a couple of ways. Now just think about this. If we have the electric field, do we have the power density? This is propagating electromagnetic fields. Do we, class? Yes, right? The E field, the H field, and the power density, we're probably getting away, are linked. One is gotten from the others. It is. We're in free space. So if we have E, I know that the power density, PF, is what? Well, it's, what is it always? I try to beat this into you.
You're at
1/2 E squared divided by 80. Y'all remember that?
Yes, sir.
All right, make sure you do. I know it's Friday afternoon, it's humid, I'm tired, we got a little coffee. So it's 1/2 times magnitude of E squared over eta. And so that's 1/2, I'm gonna just write it down for everybody. This is E squared, it's 10 to the minus third squared divided by eta, and eta is 120 pi, right? I can go ahead and do this if you want, but this comes out to what? That's 10 to the minus 6, right, over 240 pi, isn't it? Correct? And that would be the power density in watts per meter squared. Y'all agree with that? By the way, is anything going on this weekend here in Auburn? I'm just curious.
There's an art walk going on.
There's time.
Yeah.
Say again?
It's like art and Auburn or something. I heard on the
Yeah.
radio.
Downtown?
Right there. on the
Yeah, it's near.
What
Chambers.
time? This isn't for me, it's for my wife.
radio. Probably 5%.
Tell you.
Today? 4 or
Yes.
5 today? It's gonna be rainy, isn't it?
That's what I
It
thought.
says, oh, it's 6 to 10 p.m. That's what it is, and it's rain or shine.
Downtown. Is this,
Starting line party and parade 5 p.m. at Pebble Hill, downtown Auburn.
where's Pebble Hill?
It's if you're at Tumors and you keep walking up the street, it's all right there. So it's not far from Tumors.
So it's on College.
Yeah. Should have seen it.
I don't care much for parades, but I guess certain people do. All right. We got this, right? That's the E field. Now think about what I asked. What's R? Sorry, this is the power density. What did I say? How do you get the power density from anything? Any antenna? You always take the total power radiated divided by 4 pi r squared. You get the isotropic power radiation. So you take P rad, and P rad in this case I put down as 10 to the third, right?
Mhm.
Over 4 pi r squared. Right. Now, what do I do next? Short dipole, think. What do I do next? This is isotropic, right? This is, there is no focusing. I have to multiply it by the, or gain, right? Directivity, we're gonna assume directivity and gain are the same. It's 100%. So the directivity would be 3/2 or 1.5 times sine squared of theta, correct? You all agree with that? Now look. First, does everybody agree? Right? All right, now I gave you theta as 45 degrees. Do you all see that? What's the cosine of 45? 1 over square root of 2. Square that, you get 1/2, don't you, class? I'm gonna write it over here just because you might miss something. So we have 10 to the third here. We have 4 pi here. We have r squared here. Then I have, this is 1/2, and I have times 3/2, so it's times 3/4. Do you agree? Because I got theta is 1 over square root of 2, you square it, you get 1/2. Y'all agree? Right? Now, that's equal to this, right? I'm just going to equate it right here, hopefully. Y'all see, I'm just showing you how you work this problem, because this is the kind of problem I do on quizzes all the time. That's equal to this, so it's 10 to the minus 6, not much, over, I'm gonna put it as 240 pi, right? Well, we gotta solve for r, so how do you wanna solve for r? We might as well do this. This is me, I'm at the board, I can do this. You see pi goes away? Right, so I'm gonna just erase pi. And then next thing, I'm gonna multiply by 4, okay? Both sides by 4, it gets rid of 4 here, right? And if I multiply this side by 4 is what, 60, isn't it? Class?
Mhm.
Y'all with me?
Yeah.
I'm being stupid here in a way, but I want to do this to make sure everybody just sees it. What am I doing? I'm after R, so now I can multiply both sides by R squared if I want. So that means I get R squared here, right? Or sorry, I get R squared here, right? Then I can multiply by 60, divide by 10 to the minus 6, and take the square root. Or I find that R is equal to, I'm kind of curious about this one. So it's going to be 60 times 10 to the third, or that's going to be 6 times 10 to the fourth, right? That's 60 on this side, multiply both by 60. And then I have times 3/4, right? And then I have to take, that is going to be divided by 10 to the minus 6. And then I have to take the square root of the whole thing. Y'all agree with what I did? So what's that going to be? I'm kind of curious myself. I've got 10 to the minus 6 and 10 to the 4th, that's 10 to the 10th. So I need the square root of 6 times 10 to the 10th. You can just plug this into your calculators, right? Times 3/4. And what does that come out to be?
I got 2 times 10 to the 5th. But,
About 2 times 10 to the 5th meters. And that's a classic problem. How I go about using information for directivity gain to calculate a distance where the power density, well, the electric field and power density, if you have one, you have the other. I said where the electric field is 1 millivolt per meter, but it also implies power density is that. Okay, everyone? That's a pretty good, because it makes you think about all aspects of this, right? Everything. All right, now with the, I told you that for the short dipole, and this is the thing that's important, the directivity was 3/2 or 1.5 times the sine of theta. It's assuming that the antenna itself is at the origin and it's aligned in the z direction. So that's an assumption you have to remember. I'm going to mention something else. Now, I said also that this will hold, this directivity will hold for all small antennas. A loop antenna, you know that one that we got? We found that if we had a loop, you don't need to write this down, but if we had a loop antenna with a surface area S, and we come out at distance R at an angle theta, we found, oops, sorry, E field is in the actual phi direction. And E phi, and this is the wild one, because I think it's 340 the way he does it, pi to the 4th, right? And then he's got some crazy constants in here. I wish he would have, I mean, this is me personally, I like to break it down to a single number, not a sequence of multiplications, especially fourth powers. But in his book, the way he does it,
446, I think.
what's that?
It's 446 at the page 446.
Oh, formula 4.6. It's 340, and then he's going to have S over lambda squared, I believe, right? Squared. Let me get it.
320. Alright.
Oh, this is our red, sorry.
Yeah.
I'm doing it
I was wondering, it looks very.
you can, believe it or not, you can get the E field, I'm not gonna mess with it right now, you can get total power radiated, take
Go
this.
back there.
Yeah, I'm not gonna go do it backwards, but in his
Okay.
3.6,
That's, angular velocity.
I'm not even gonna mess with you. He gives you the radiation resistance as 320 pi to the fourth S over lambda squared. Sorry, that's what I should have done. This is R rad, right? And remember, S is the surface area, so it's pi a squared. That's the surface area of the. Now that's the radiation resistance in ohms. But for, this is the small loop. This is the small loop. And I make the case small loop is when the perimeter 2 pi a is less than lambda over 10. He just says it's small. Right. It's where you take the total length around there, straighten it out and said if that looked like the length of that has to be less than 1/10 of a wavelength. So, I mean, this is kind of one of those things. This is a rule of thumb. Is there an abrupt change? If you actually look at the E fields as this thing gets longer and longer, or the radius gets larger and larger to given frequency, not really that abrupt, but there is a noticeable change. And the directivity will be the same. So the directivity for this short or small loop, the directivity is 1.5 times the sine squared of theta. They're the same. And this is assuming that it's oriented in the X, Y plane and it's perpendicular to the Z-axis. In other words, it's concentric with the Z-axis. That's all it's staying. Those two are the same. So the next antenna we talk about, and remember, I gave you formulas. If you have more than one loop and you want the actual radiation resistance, you really just take the radiation resistance of one loop and multiply it by the number. All right, you have, that's it. And if you want the E field or H field, it's just multiplicative. That's all it is. I mean, you take it times the number of terms. But this is going to be a very small resistance. And you need a lot of terms to get something so that you get a meaningful resistance, so your radiation resistance is higher. Now, after those two things, the next thing we do is talk about a straight wire antenna of arbitrary length. I'm going to start right here, and I want you to please write this down because this is important. So now this is a straight wire antenna. But now it's long. So now the length is going to be greater than 1/10 of a wavelength. So here we go. Now I have an antenna with a total length of L, and it's going to have some current I going into it, I not in there. Some will go up, some will come out this way. All the current will be in the Z direction of, this is the Z axis. Okay? Now remember I told you in order to calculate the electric field or the magnetic vector potential, I'm not even going to bother with the magnetic vector potential here. I'm going to get the differential electric field. What you need is the current anywhere on the wire. Do y'all remember that? All right. There's only one, you can't solve this mathematically for the current in the wire in terms of a closed form solution. What you have to do is an iterative approach. But the nice thing is it does have a mathematical approximation. If you assume this is centered at the origin, this is minus L over 2. That's the bottom. And the top one is going to be at L over 2. Remember, we're in the Z direction. Total length L. The actual current on this wire, anywhere on the wire, is going to be a function of Z. And I'm just going to try to draw it. If this is the magnitude of current going this way, I don't know what kind of does this. What you'll see is the current has to go to 0 at the ends, because this is a real antenna. It's not the differential, it's a bit fictitious, sorry. Now, it has to go to 0 at the end, and we'll have something like this. You don't know if it's a maximum at the center or not, but it'll be symmetric about the center. Do y'all follow me? The formula for this, I of Z, is given in the book, and it's I naught. Well, you know what I naught is. It's just scalar value. It's the value of the current that's feeding that antenna right at the junction where it's connected. There's some kind of a voltage source here that's driving that antenna with I naught. It's I naught. Then it's going to be times the sine, and it's important you write this down. And then it's going to be beta is 2 pi over lambda, times the quantity L over 2 minus the magnitude of Z. Here, I've got to make some comments before we continue. And again, that came up with an iterative type of approach. Yeah.
Is Z the distance away that you're measuring?
Z is going to be up and down this axis. Here's Z. This is at 0, so at any point on here, it would be Z. Now, just follow me on this, because it's important. When you're at the end of the wire, the current has to go to 0, doesn't it? I made that statement. It has to, actually. Mathematically speaking, if it doesn't, I mean, you could argue whether it could be a blob of charge there that's getting bigger and then going down. In fact, yeah, that's a little of that, but it's an extremely small amount. All right. And if we have that, well, what happens when Z is L over 2? You get 0 here, don't you? Y'all see that? L over 2 minus L over 2 is 0. 0 times anything is 0. Sine is 0, 0. It does. Now make Z minus L over 2. Well, L over 2 minus magnitude of minus L over 2 is just L over 2 minus L over 2. It goes to 0, right? All right, so what is it at the center? Well, at the center, it's the sine of beta L over 2, right? Now hear me. That does not have to be 1. Y'all follow me on that? Think about it now. At the center, and you can write this down. At the center, and that's Z equals 0, I of Z equals I naught. Now that I naught is the current that's feeding right here. This is where it gets a little crazy. Then it's going to be times the sine, right, of beta L. Well, beta is 2 pi over lambda, right? Divided times L over 2. So that's equal to I naught times the sine. Oh, and now it's going to be pi L over lambda. Just work with me on this one. Y'all follow me? This is the thing that's going to bother me. Okay. Now, what you would say is if you have an antenna like this, then the current here, I naught, should be the current right here, just as you turn that bend, right? That's intuitively what you'd say. Not quite true. Take a look at what happens. Suppose L is equal to lambda. Just take a look. Now the total length of the antenna is 1 lambda. Then I get lambda, right? By lambda is 1, correct? And I have the sine of pi. What's the sine of pi? 0. Now it never really goes to 0. But it gets, what really happens, the current tends to a very low value. It means that the impedance of the antenna will be very, very high. Y'all follow me? So when you have he doesn't bring this out in the book, when you have an antenna, it's a full wavelength long. You'll feed some current in there, but it's got very high impedance, which is some ways you want that. The problem is the actual beam pattern then has 2 big lobes, and you can't distinguish radiation that's reflected and comes back from the top one versus the bottom one. So even though it's got a great radiation resistance, it's got a horrible beam characteristic. Y'all with me on that, class? And that's just something to remember. You'll see more of this. He doesn't bring it out in his book, but I want you to know. So you can see that when it's exactly a full wavelength, that the current theoretically goes to 0 right at the top, the feed. It never goes to 0, but it gets low. And by the same token, if it's half, or if the current, if your antenna is equal to lambda over 2, just take a look at this. If it's lambda over 2, right? It's when Z is 0, right? If Z is 0, we're going to take a look at that current. Then I have lambda over 2 over 2. I have lambda times beta. And I'm trying to do this. This is going to be the sine of pi over 2, and that, in fact, will be 90 degrees. Sine of 90 is going to end up being 1, isn't it, class? All right, so remember that if it's a half wavelength antenna, then you're going to have I naught will be the feed that goes up the antenna, but you don't have to worry about that much right now. Anyway, this is the antenna. This is the current along the antenna. And here's the way we do this problem. Some of you probably looked ahead and know this. The way we do it is this. If we have an antenna with a given length, L, we're centering this at 0. That's the z-axis. Now if I have a point here that's at a position, Z, and it has a current right here, and the current is I of Z. Now I know what I of Z is because that's it, right? And this is at a constant frequency. Then what I do is, and you're going to have to just go with me on this, I'm going to erase that thing. I'll put it here. I'll make one other comment. In his book, he doesn't have L over 2 minus magnitude of Z. He says for Z greater than 0, it's beta times L over 2 minus Z. For Z less than 0, he'll have L over 2 plus Z. So I put the magnitude there because it's more compact. All right. Now, if I have this differential length here, I have really I dz here. Y'all follow me? That looks like a dipole antenna. It looks like a short dipole, doesn't it? With length dz. So I can say if I come out a distance r prime, that the differential electric field from that, dE, would be equal to J eta beta times I of Z times dz over 4 pi r. Now here I'm replacing the I naught times L with I of Z times dz. Y'all follow me? Then it's going to be times the sine of theta, just like it is for a infinitesimal or a short dipole, Hertzian dipole. And there'll also be e to the minus j beta r, and this will be in the a theta direction. Now I'm making a few assumptions. I'm talking about the far field, so we're assuming r prime is much greater than the length of the antenna. You're out there, boys. This has nothing to do with near field. This is a launched wave propagating. And I'm just taking this thing and made it look like a little antenna, a short antenna. Now to get the total electric field, you got a whole bunch of little antennas. And y'all remember when you had calculus, one thing they talked about is the building block. I call it the building block approach. Only thing I'm going to do is either sum up the electric fields from all the little chunks, right? Or integrate them, right? Because the integral is really, the limit of the sum is the deltas go to 0. So now I take this, and if I want the total E field, this is going to be a little troublesome. Boom. Just bear with me, guys. So that's the differential field from an arbitrarily long antenna. Then if I integrate this, I get the E field, and this is integrated from minus L over 2 to L over 2, L over 2, minus L over 2 to L over 2. Here's you got to pay attention. This is just, I don't give you problems and beat you up on this one, but you have to kind of appreciate this. Now this distance I have is r prime. I should put in r prime there. Prime that. That distance is measured right from the point where the current is. It's giving rise to that differential field out there. Out here, the BE. But this problem lends itself to spherical coordinates. So there is actually an R vector right here. Y'all follow me? Pay attention to this. These two, since I'm a long way away, the R prime and the R are parallel. Y'all see that, class? You get far enough away, they're parallel to each other. And because they're parallel, if I'm at a height Z here, then the distance difference between R prime and R would be this distance. Can you all see that? Are you with me? If they're parallel, right, then the real length difference is going to be this one shorter by that much. And this distance here, right here, would be Z times the cosine of theta. And again, this is theta right here. Can you all follow me? He's got this in his book. Take a good look and just understand. So, that said, now I can come down here and I can say that R prime, this one that I have, is really equal to R minus Z cosine of theta. This is consistent with Dr. Wentworth's book. Do y'all agree with that? Assuming we're far enough away. And here's where I have to be careful. Make sure I keep you guys, everybody sees this. Now, this term Z cosine of theta is small compared to either R or R prime. With me? It's trivial. And what that means is, when I take a look at 1 over R prime, it's about equal to 1 over R. No difference. Think about 1,000 yards and 1,000.1 yards. Take 1 over either, it's about the same, right? With me, class? This is where it's important. So that means for this one right here, I can replace that by R. That's the actual coordinate system of these spherical coordinates. Y'all follow me in that? Because 1 over that. So I just replace that by R. But it gets a little interesting up there with the beta R term. This is where the real mathematics come in. When I look at this right here, and that I of Z I didn't put in there, well, beta R right here is really beta times, and I should say R prime, is beta times R minus Z cosine of theta, isn't it? I'm just replacing the R prime with R minus Z cosine of theta. Y'all with me? That's equal to beta R minus beta Z cosine of theta. Okay? Now here's what I'm about to do. If you're all with me, right? I'm going to take this quantity and stick it up there for R prime, or beta R prime. But I'm going to do one other thing. I'm also going to factor out the J eta beta 4 pi R, because R now is like a constant, because I'm integrating dz. It doesn't change versus theta. So I take that out in front. I've got J eta beta 4 pi R out in front. I can take the sine theta out in front, because that angle is going to be assumed constant, all right? But I'm going to leave in the I of Z business. So I'm actually going to get this. I'm going to get J eta beta, right? And then I'm going to have 4 pi R. I'm going to have the sine of theta. And then the I of Z is I naught times that. I can take the I naught out in front. And now I'm left with this. I have the integral from minus L over 2 to L over 2 of this. The I of Z, I took the I naught out, but there's the sine of quantity beta times L over 2 minus the magnitude of Z, right there, times e to the minus j. And here I'm going to break this up into these two things. E to the minus j beta r, right there, times e, and then it would be plus j beta, let me bring that down a little, times e to the plus j beta z cosine of theta, and it's going to be dz. Now, I did it this way in Whitworth's book, Dr. Whitworth's book. he shows what I'm doing, if I can find it. He shows you the current thing on page 449, and he shows you the currents that he adds an additional possible phase e to the j alpha, but don't worry about that. It doesn't help in the discussion, but he gets down to that integral in equation 870 that I've got up on the board. It's just, he does the H field. So if you multiply that by 8 and 9, you got mine. Y'all sit? Okay, now keep listening now. This R right there is measured from the origin, does not vary with Z. Y'all with me?
Mm-hmm.
I can take the e to the minus j beta R out in front, and I'm going to do it right here. So I get rid of it there, and I'll put the I naught out in front. All right. Now when you look at this, this is where the dz integral, where we get into some fun, right here. I can do this a couple of different ways. One of them, I can take that sine, at least if possible, but I think Dr. Wentworth does it a different way. You know how the sine of theta is equal to e to the j theta, and it's minus e to the minus j theta over 2j. You all remember that? That's Euler's identity, right? So you can take that sine, you can break it up as e to the j beta times L over 2 minus magnitude of z minus e to the minus j beta quantity L over 2 minus magnitude of z over 2j, and then multiply it by this. And then what you're going to see, you collect the coefficients of the exponents, and you can do the integration. That's one way. Another way, if you're so inclined, you can take this and turn it into a sine and a cosine, because e to the j theta is equal to cosine theta plus j sine theta, right? So you can make this cosine of beta z cosine of theta plus j sine of beta z cosine of theta, and then you've got a couple of trig intervals. You can do it either way. I'm not going to ask you to do that, but you have to be aware of the way it works. You can, and by the way, you got your homeworks to turn it through, don't you? Is that what you were working on back there?
No.
It doesn't matter.
It sure looks good.
So I'll tell you what, you just hold them until I give you the quiz, and I'll grab it. But do you all follow me what I'm doing here? Now, after you turn the crank on this mess, doesn't matter which crank you turn. I mean, I can do this in class, but honestly, it's about a 10, 15-minute waste. All right. If we do this in class, what you'll find out is that E has the H field, will be equal to J eta, and then the way he does it, he's going to have, it's J eta divided by 2 pi R here. Times I naught. This is the E field. He doesn't have this. He has H. Times I naught. And then you're going to see this. There's an angular function, and it's going to be cosine of beta L over 2 cosine of theta minus the cosine of beta L over 2 divided by the sine of theta. And he has that angular form in equation 8.71, and he has a square of that in 8.47. Now that's after you do the integrations, and this is in the A theta direction. This is assuming that the antenna is aligned with the z-axis of length L. Y'all with me? Here in this one, the L is the length of the antenna. And I'm going to tell you, this itself is the E field. To get the power density, average power density would be 1/2 magnitude of the E field squared over eta, right? We could get, you all know what I'm talking about, right? Then we could go ahead and integrate the power density over the whole thing, get the power radiated, we could find the radiation resistance, and we can get the directivity. Here's the problem with this one thing, just listen to me. This is an angular function, right? Before, our angular function was sine of theta, right? By looking at it, I knew it had a maximum value of 1, right? So I knew the normalized power density would just be that. Are you with me on this? I mean, it would be just sine of theta, or sine squared of theta, pardon me. With this one, this thing will have a value possibly greater than 1, a lot greater than 1. So now, in order to get the directivity, you have to find the normalized power density, and I'm going to try to make this clear to you. Anytime you have an E field or an H field that has an angular function like this, the power density will be proportional to that angular function squared, always. Y'all with me? Because power density is 1/2 magnitude of E squared over eta. If you wanted to use H, it would be 1/2 eta magnitude of H squared. It's always proportional to this angle squared. Got me? Period. And what Whitworth does, if you look in the book, you all have your books there. If you look at equation 8.74, he goes ahead and he says that you can find the actual power density. Wait a second. That's power density. Put down in 8.73, he doesn't write this down. He says average power radius. That's a misnomer. It's power density. The unit should be watts per meter squared in 8.73. Do you see that, class? Just make a note. All right, it should be watts per meter squared, but he has the F of theta as this squared. So I'm going to talk about that for a second. So if I have this antenna, after you do the mathematics, I'll talk more about the ones we really use, the equations and stuff is really coming back. So if you have this, there's one thing that's important, it's the average power density. If you got that, you have the E field, don't you? Right? So his book shows you this. Put it down as PAV. PAV from an arbitrarily long antenna, and he'll have it as, I think it's 15 I naught squared. I want to make sure I keep the form because, yeah, that's it, over pi r squared. All right, and then it's going to be times F theta right there. But his F theta is equal to my, the ones we got for E and H squared. So it's cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 divided by the sine of theta, and it's squared. You take a look in his book. I'm glad you guys have your books. Y'all with me? There's what's nice about this. If I've got this, I know the links to the antennas, right? I mean, you're going to have could be a lambda antenna, it could be a wavelength long, half wavelength, 3/4 wavelength, doesn't matter what it is. Now you know the angular variation, y'all with me? And I can get the average power density right there by taking that thing and squaring it, okay? The gain calculations, it was where it gets a little problematic, because if this is the power density, right? And I want the value normalized, so the maximum possible value is 1, right? When we do directivity, let me say it that way, directivity calculations, D max, right? I know what I need is 4 pi over that double integral of the normalized power density times the sine of theta d phi, right? Now, I mean, this is going to go, theta would go from 0 to pi, and phi from 0 to 2 pi. But I need, normalized means the biggest possible value is 1. Are you with me, everyone? Well, you've got to find the maximum value of this first and then divide that maximum value into this to have the normalized power density. Do you all see this? Because when you look at the power density, this is the power density, we want normalized. All that stuff there doesn't matter. The only thing that matters is F theta, right? So that means the normalized power density for that thing would be F of theta over F max, which you don't know. So each time you have one of these things, you've got to calculate F max first, then divide it into F naught, and then you'll have the normalized power density. Then you do this to calculate the gain, but don't worry about that. I'm not going to ask you to do that. Are you with me on this? There's no shortcuts to a lot of this, unfortunately. But that's all right. There are some standard sized antennas that are used everywhere. The first of the straight wire antennas is the half-wave dipole. Have you all heard of a half-wave dipole? No, well, a half-wave dipole is just half a wavelength long. And the beautiful thing about it is it has it has a high radiation resistance, and it has beam characteristics that we kind of appreciate. Trust me on this. Dipole antennas are used everywhere. I don't think they use them anymore, but does anybody have an old stereo receiver at home? Well, they have a folded dipole antenna. They'll have something that looks like a T that's usually included. You ever see those? I'm really old. I remember those. When I was younger, when I was where you were, one of the things that was popular was really high quality, high fidelity sound systems. And you would talk about amplifiers made by like Acaia or let's see, Sherwood, or I'm trying to think of some of the other ones. I can't even think of some. But anyway, there were all these famous brand names. And there were famous brand names for speakers that had very good characteristics in the frequency domain, could represent the sound. One of them was Bose. Remember, he was a professor at MIT. I'll tell you a story about that. I may have told you had me for signals, right? Remember you telling a story about Bose? All right, he was a professor. He got fed up with what was out there. He was a young professor. So he built his own speakers. He started marketing. He made a fortune. And he was a clever guy. He took cheap speakers, but he had a sound system that amplified the sound from your stereo system in a way that it would give completely flat response. So the low frequencies would have the same amount of power output as the high frequencies. That's what you want. Most speakers don't do it because the cone has inertia. And so the faster you want to vibrate, right, the more inertia and the less power you actually get radiated. And I'm not going to go there right now, but Bose solved that problem by just creating a function. It's the inverse of the characteristic power versus frequency. Took one over that and multiplied so he has flat, and it's one all across. He's a smart guy. And he marketed, but it takes an active crossover. There's a lot of other things that are done. And these are engineers that get fed up with what's out there. That's what it comes down to. Because most musicians and people like this, they don't have an appreciation for how to make something sound better unless they have a technical background. Okay, now we get into, about out of time, but I'm going to just tell you this. We're going to get into the most common straight wire antenna. It's called a half-wave dipole. As you might gather, a half-wave dipole is a half-wave length. So here, the length becomes lambda over 2 total length. Okay. Now this is significant because if the length becomes half wavelength, then when you look at the E field from this, I'm not going to back up and get to the formulas. It will be J times 60I. Just write this down. I got rid of the 2 pi's. I took the eta beta crap and I got rid of all that junk. It's just 60I. Whitmore's book doesn't have this. 60I over R, and R is the radial distance. Then it's going to be times the cosine of beta L over 2, and really it's cosine of pi over 2. I'll get to why that's the case in a second. Cosine of pi over 2, cosine of theta, all over the sine of theta. Now this is for a half-wave dipole, and that's A in the theta direction. And I'll write this down now. He doesn't have this, he has H, and he'll have Ji over 2 pi r. That's what he's going to have in his book. It'll be in the phi direction. For a half-wave dipole, this is really nice stuff here. It's easy. Why is this the case? Because remember, for the arbitrarily long dipole, you had an angular function, f of theta. It was really the square root I'm about to show you, but you had an angular function, I'll call it small f of theta, equal to cosine of beta L over 2 cosine theta minus the sine, or sorry, minus the cosine of beta L over 2 divided by sine of theta. Do y'all remember? That was the entirety of that integral, right? The arbitrarily long dipole. Well, here, when beta, think about this. I said it's a half wavelength long, so beta L over 2, beta is 2 pi divided by 2 times L is lambda over 2, right? So that's pi over 2. Do y'all agree with that? So if you take pi over 2 and put it in here, you have pi over 2 cosine of theta. But then when you put pi over 2 here, right, where beta L over 2, what happens? It becomes cosine of pi over 2, or cosine of 90 degrees, which is 0. Y'all with me? So this part goes away. That's nice. Now that is the electric field, right? Here's another nice thing. See this angular function right here? It's got a peak value of 1. It's already normalized, in other words. So you can calculate the directivity, the maximum directivity very easily, okay? I want to give you your quiz and give you enough time to do it, but we're going to pick that up on Monday, and I'm going to go through the complete circuit, and I want to spend a little more time doing more problems, really tossing at you different things, so you'll have more of a feel for it. Okay, here comes the quiz. Take everything off your desk, except you can use a calculator if you want. I don't think you're going to need one. And do me a favor, print your name, please. I can only tell you, I'm so thankful there's only a few students in here and we have decent handwriting. Because when you have 90 to 100 students, all it takes is about 1 or 2 to really mess that day up. Sorry. Yeah. You can see. Oh, yeah. Take your homework out too. Make sure your name's on it. Thank you. Thanks. Anybody else have homework? Oh, thank you. I got you. Thank you. It might have been irritating, but it was doable.